Safe and healthy. This week we will be talking about strong induction, and the theory for this discussion section is pretty low, but we'll be looking at a couple of actually three questions, which would give us a really good insight into how we can use strong induction and how it is different from the principle of mathematical induction that we learned in the previous lecture. Um, just something more administrative. Please make sure you use ECS 20 in your subject line whenever you're sending me an email. I filter every night and I just don't want to miss any emails and get back to you as soon as I can. So, yeah. There's a book that could be interesting to you that's called Discrete Mathematics with Ducks, where they go through all the concepts of discrete math with examples of ducks and like a group of ducks. I don't know what a group of ducks is called now, but yep, and just a small thing to get us started. All right, so let's get into the definition of strong mathematical induction. So, the strong induction principle states that you can prove a statement of the form Pn holds true for each positive integer n, that is, some statement Pn is true for all positive n, by proving the base case, that is, P1 is true, and assuming that some number of integers would also satisfy the proposition Pn, that is P1 till Pk, and then using those results we can prove that Pk plus 1 is true. That is, what in principle of mathematical induction, what we used to do is we used to assume P1, we used to prove P1, assume Pk, and prove for Pk plus 1. What here we are doing is we proving P1, assuming from P1 till Pk all the statements are true, and then from those results we'll be proving Pk plus 1. Loop back to the um, definition of proofs that we were talking about in the earlier discussions, that a proof is just using your existing knowledge to narrow down to a conclusion. So right here you have existing knowledge and you'll be getting down to a conclusion, that is Pk plus 1 true or not, right? So yeah, this is the principle of mathematical induction. You just need to prove Pn um, for each positive integer n. The base case is P1 is true, so you prove that, assume that P1 till Pk also hold true, and using these results you prove for Pk plus 1 that is true. So it's similar, like if you can take the first step on a ladder and assuming you can take steps up till k, you can climb the k plus 1 step as well. So that's the principle of mathematical induction. Or like if you go into the domino principle, the first you fall the first one falls down and the next k digits will fall, and that's when the k plus 1 will also fall, right? So that's the principle of strong induction. Let's look at a couple of prime number definitions for us to solve the next question. Um, so if you're given two integers a and b, we say that b divides a if there is an integer q such that a is equal to bq. That is, a is divided by b, leaving a quotient q and no remainder, right? So we know that 4 divides 8, so that's a divides b as b divides a as a is equal to b times q, where q here is 2. 3 divides 51 as 51 can be written as 3 times 17, right? So the first definition is, given two integers a and b, we say that b divides a if there is an integer q such that a is equal to bq. Next, an integer p that is greater than 2 is called a prime number if the only positive integers that divide p are 1 and p. That is, the factors of that number are just the number itself and the number 1, no other factors. So is 21 a prime number? No, because 21 can be written as 1 times 21, 3 times 7, 7 times 3. So it has factors other than 1 and and the number itself, so it's not prime. The number 17 is prime here because it has no other factors other than 1 and the number itself, right? So, yep, that's the second definition. So, an integer p greater than 2 is called a prime number if the only positive integers that divide p are 1 and p itself. Yep. Next is, if an integer c is greater than 2 is not a prime, so that it is a composite number, then there exist integers a and b with a comma b is greater than 2 but is less than c minus 1. That is, if you have a number like 21 again, you could write it as 1 times 21, 3 times 7, and there exist integers a and b. So there are integers 3 and 7 for which 21 could be written as 3 times 7, right? So that's a composite number. So the result is, if an integer c greater than 2 is not a prime, then there exist integers a and b which are greater than 2 and less than c minus 1, such that c can be written as a times b. Alright, so now what we want to prove here is that every integer that is greater than 1 can be written as the product of prime numbers. That's the theorem of the fundamental theorem of arithmetic, that every integer greater than 1 can be written as the product of prime numbers. Which is also, Pn is the statement that n can be written as the product of prime numbers. We can rewrite this. So Pn is true for each integer greater or equal to 2. Because greater than 1, we just wrote it as greater or equal to 2. So the base case is 2. We know that 2 is a prime because it can just be written as 1 times 2, and it is a product of a single prime. The strong inductive step. So suppose for some k that is greater than 2, that each integer n with n where n is greater than 2 but less than k may be returned as a product of primes. So that's what we are assuming here, and we need to prove that k plus 1 is a product of primes. That is the next integer from k, right, is a prime. So first case, suppose k plus 1 is prime itself, we are done. We can write it down. But if k plus 1 is not a prime, that it is a composite number, then by the fact stated above, there exist integers a and b where a and b are less than 2 but greater than 2 but less than k, and they can be written as k plus 1 times ab. If you loop back to the third definition right here, what's the definition one? Right here. If an integer c is greater than 2 is not a prime, then there exist integers ab with which 2 great so ab is less than c minus 1 but greater than 2, right? And we used it right there, where the first case was that k plus 1 was a prime, so we are done. K plus 1 was not a prime, so we could write it as a product of prime numbers, and we can iteratively say that a comma b can also be written as prime numbers to show that it is a product of primes. And so thus k plus 1 is also a product of prime, and we're done by strong induction. Take a look back what I just said, and if you have any questions, please ask me. Okay, next question is, prove that any integer amount of postage from 8 cents or upwards can be composed from 3 cents and 5-cent stamps. So what I'm trying to say is that if you want to talk about 15 cents, then you can have 3 coins of 5 cents each. If you have something like 48 cents, you can have, at least there is one way possible to write it down. So 48 cents can be written down as 16 times 3 cents, or I could write them as 6 5 cents and 6 3 cents, right? So there is at least one way to show that an integer amount of postage from 8 cents or upwards can be composed from 3 cents and 5 stamps. So using a combination of, I have an infinite supply of 3 and 5 cent stamps each, and I just want to show that it is possible to have any number possible. So if I have to send a postage which requires 17 cents worth of it has to be worth 17 cents. The stamp has to be worth 17 cents. So I can do something like, what can I do for this? So 4, 3 cents, and 1, 5 cents, right? This is possible. All right. So how do we go around proving that this is always the case, that any integer above of postage from 8 cents upwards can be composed from 3 cents and 5 stamps? So with a strong induction, we can make the connection between Pn plus 1 and earlier facts in the sequence. That's what we were doing. We were assuming so we were proving the base case, assuming all the results from P1 to Pk and then proving for Pk plus 1, right? So here, can you say that Pn minus 2, that is, when I'm saying that money, the stamps worth n minus 2 and money worth n plus 1. So that's basically something like um, 15, sorry, 15 and 18. And I can write 15 as 3 into, so 3 stamps of 5 cents each. Can I write 18 as 3 times 5 cents? So that's the same thing as 15, but I add one 3 cent stamp in that, right? If I had 21, let's do 22, right? So if I had 22, what would I have? I would have taken two 5 cent stamps and uh, four 3 cent stamps each. If I had to show 25, can I just put it as 2 times 5 cents, the same thing as 22 cents, and just add one 3 cent stamp in there? Does it make sense? So each time I'm looking at n minus 2 and n plus 1, all I'm doing is that in the Pn minus 2, I'm just adding one 3 cent stamp in that to get the Pn plus 1 solution, right? So yep, so let's use this fact. That Pn minus 2 is relevant because Pn plus 1 can be composed from the solution for Pn minus 2 plus 1 3 cent stamp. Alright, so let's prove the base case, that is P8, because we have shown that any integer amount of postage from 8 cents or upwards. Alright, so to prove that 8 is possible, you just use 1, 3 cent and 5 cent, just show that it is possible. So the base case is proven. The inductive step states that proving from 8 till n, we need to prove Pn plus 1, right? For all integers n greater than 8. So let's find P of 9 and P of 10 here. So P of 9 would be 3 times 3 cents and P of 10 would be 2 times 5 cents. Now, let's look at K plus 1. So K plus 1 would be 11 now. And 11 can be written as the solution from um, 11 can be written as the solution of P8 plus 1. P9 can be written as the solution of, sorry, let me just write it down here. And so on. So using the previous results, P8, P9, P10, I can keep on recursively saying that P11, P12 till any number can be written as the sum of or as the result of a previous one, right? Alright, so for Pk plus 1, for all integers, all natural numbers n plus 1 greater than 10, the inductive hypothesis entails the proposition Pn minus 2. If Pn minus 2 can be composed from 3 cents and 5 stamps, then n plus 1 cents can be composed from 3 cents and 5 stamps simply by adding one more 3 cent stamp each to that, right? So the inductive proof leads directly to a simple recursive algorithm for selecting a combination of stamps. Notice also that the strong induction proof may require several special case proofs to establish a solid foundation for the sequence of inductive steps, and it is easy to overlook one or more of these. That is P9 and P10 that we tried to find out, right? Alright, that was a good question. Next question is, to prove that breaking a chocolate bar with n with more than one or more or equal to 1 pieces into individual pieces requires n minus 1 breaks, right? So what is the question? You're breaking a chocolate bar into n pieces, and you'd require n minus 1 breaks for that, right? So that is, Pn is, breaking a chocolate bar with n greater than 1 pieces into individual pieces requires n minus 1 breaks, and we prove Pn holds true for all natural numbers n with n greater than 1, greater than or equal to 1. So understand the statement that I'm making here, that Pn is, breaking a chocolate bar with n greater than 1 n pieces into individual pieces requires n minus 1 breaks. There are n pieces and you're breaking it into n minus 1. Sorry. The chocolate bar is of n pieces and you're breaking them into individual pieces and will require n minus 1 breaks. The base case, you just want one piece, and so for just to get one piece of the chocolate bar you don't need to cut it down. That's 0 breaks, so that is P1 requires 0 breaks, and that is exactly n minus 1, that is 0, right? So we can say P1 holds true. For the inductive step, assume that for some natural number n, where n is greater than 1, but and also for another natural number n dash that is less than n but greater than 1, that Pn dash is true, and for any candy bar with n dash pieces requires n dash minus 1 breaks. So we're assuming here for the inductive step, we will prove for Pn. So we've assumed for all the integers from 1 till n that it is possible, and we will prove Pn that breaking any candy bar with n pieces requires n minus 1 breaks. Right? So to see this, consider any possible break made in the candy bar. This will split the candy bar into two pieces. So any break that I do will actually divide into two parts, one of size k and one of n minus k, because I'm just assuming that it could be any cut from anywhere on the candy bar. It could be exactly half, it could be at any other proportion. So also note that n minus k would be less than n but greater than 1, and since the second piece is not empty and is not the entire candy bar, so it will have two parts. So any cut, any break I make will divide into two parts in any proportion, but there will be two parts of the candy bar after I break something, right? Since k is less than n but greater than equal to 1, breaking the k piece candy bar requires k minus 1 breaks. And since n minus k is less than n but greater than equal to 1, by our inductive hypothesis, it will require n minus k minus 1 breaks. So it's a recursive thing where you're talking about the whole n piece candy bar, you're dividing it, and then you're saying that according to my inductive hypothesis right here, that for any n dash with which is less than n but greater than 1, Pn dash will hold true, and the candy bar will require n dash minus 1 breaks. So I've assumed this result, and for any number that is less than n greater than 1 equal to 1, this result will hold true. That is, it will require n dash minus 1 breaks. So that is exactly what is going on here, where I'm saying that I've broken the candy bar once, that is 1 break, and I'm getting one with k that is less than n, and another one that is n minus k, which is again less than n. So I can use those results to say I need k minus 1 breaks and k minus 1 breaks. I just bold this right here, right? And that one of breaking them into these. So I have k minus 1, that's this one right here, n minus k plus 1, that is to break the candy bar with n minus k pieces, and plus 1 to break the n candy bar, sorry, to break the n piece candy bar into k and n minus k, right? And when you add all the breaks that you took, it is n minus 1 breaks for the n piece candy bar. So this was a really interesting question when I was trying to solve it, because it's actually you recursively looking at it, that first you're making the first cut and then it's just going down into your inductive hypothesis results that you were talking about. So yeah, this is an interesting question. Okay, next is, every third Fibonacci number is even, that is for all numbers n greater than 0, greater than equal to 0. If fn is even, then fn plus 3 is also even, right? So that is every third number is even, or every fourth number. Let's see what I'm talking about. So the Fibonacci series is 0, 1, 1, 2, 3, 5, 8, 13, and 21, and it goes on. For people who don't know what Fibonacci numbers are, so this is the first number. So it's a series of numbers. The first number and the second number are 0 and 1 always. The third number is the summation of the first and the second number. So the previous two numbers. Now 2 becomes the summation of the previous two numbers, that is 1 plus 1. Third is 2 plus 1, that is the previous two numbers. 5 becomes the summation of 3 plus 2. 8 becomes the summation of 5 plus 3. 13 becomes the summation of 8 plus 5. And 21 becomes the summation of 13 plus 8. And it goes on, right? So what we are saying is that every third Fibonacci number is even. So right here, that is Fn, Fn plus 1, Fn plus 2, Fn plus 3. So it's even. So if Fn is even, Fn plus 1, Fn plus 2, Fn plus 3, that's 8 is also even again, right? So that's how what we're going to prove, that if Fn is even, then Fn plus 3 is also even, and actually vice versa, that if Fn plus 3 is even, then Fn is also even, right? Let's look at that. The base case here is for both n equal to 0 and n equal to 1, because here that we see that f0 is 0 and f0 plus 3 is 2, and both are even, so it holds true. But for n equal to 1, we see that f1 is 1 and f4 is 3, and both are odd. So in either case, we've proven the predicate that fn is even if and only if fn plus 3 is even, right? So use two base cases here using 0 and 1. The inductive hypothesis assumes that P1 till Pn are true. In particular, this means that Pn minus 1 and Pn are both true, right? You see what we did here. We assumed from P1 till Pn, and then we meant that Pn minus 1 and Pn are both true. So when I said that, inductive step would be, if A and B are integers, then A plus B is even, given that A is even and B is even. Try to prove this. If A plus B is even, implies that A is even if and only if B is even. Okay? Look at the brackets that I've used here just to make sure you know what you're talking. Anyway, okay. So next, now consider that fn plus 1, and let's see, if fn plus 1 is even, then we have to say that fn and fn minus 1 both are even. If fn is even, that implies that fn minus 1 both of them are even, and fn plus 3 is even, then fn plus 2 is also even. So what we effectively did here is that, looking at the definitions here, we said that fn is even, fn minus 1 is even, imply if and only if fn plus 3 and fn plus 2 are even as well, right? So the final equivalence holds by the inductive hypothesis because we have assumed that Pn and Pn minus 1 are both true. Continuing the above is equivalent to fn plus 3 plus fn plus 2 is even. So that is fn plus 3 and fn plus 2 both are even, implies that fn plus 1 is also even, fn plus 4, given that fn plus 1 was also true, was also even. So we've shown that fn plus 1 is even if and only if fn plus 4 is even, which is exactly the statement Pn plus 1. I would ask you to pause it right here and try to read the slide that is up there and understand what is going on and where, right? Something called the well ordering principle. The principle states that any non-empty set of non-negative integers has a smallest element. That is, if you take a subset of the natural numbers in a set without the smallest element, it will be empty. So that is, every non-empty set has a smallest element in it, right? So to we can use well ordering principle to prove a few results. So let's start by understanding how we can do it. So let Pn be a statement involving a natural number n, and we have to prove that Pn holds true. So to prove that, we'll begin by letting S be a proposition that for all n, for an n that belongs to a natural number, Pn is false. So what we did here is, make sure you look here, that for Pn for like n natural number n, the proposition is false. That's what we wrote here, right? Next, I'll just bold this here again so that we have it in our head. Alright, next we argue that there is no smallest element of S by doing a proof of contradiction. So we'll see, you'll understand it better as we go down. Suppose that S has a smallest element n. N is the smallest natural number for which Pn is false. We obtain a contradiction by following the following two steps. Step 1, show that n is not equal to 1 by showing P1 is true. So we have assumed here that n is the smallest natural number for which, oh, where is my cursor? Yep. So n is the smallest natural number for which Pn is false, right? So we can say that n is not equal to 1 because P1 is true. So you prove that P1 holds true, and you can say that actually P1 holds for P holds, the proposition holds for 1 and n cannot be 1. Now show that n cannot be a natural number greater than 1 by proving that not negation of Pn implies negation of Pn minus 1, which contradicts that n is the smallest natural number for which Pn is false. So you assume not P of n, you prove not P of n minus 1. Did you see what we did here? We assumed not P of n and we proved not P of n minus 1, which contradicts that n is the smallest natural number for which Pn is false. So we had two contradictions. And finally, we conclude that since S is a subset of natural numbers with no smallest element, because if not P of n implies not P of n minus 1, that means n minus 1 is the smallest element, but we assume that n was the smallest element. So that contradiction holds, and Pn is false is a contradiction. So we conclude that S is a subset of the natural numbers with no smallest element. The well ordering principle implies that S is empty and hence Pn is true for all natural numbers n. Alright, one question is, try to do this using the well ordering principle. Prove that if n is a natural number, then 2 does not divide 3n squared plus 5n minus 1, right? And that's today's discussion section. We'll just go over real quick. Make sure you have ECS 20 in the subject line when you email a TA. Please make sure of that. We defined the principle of mathematical strong induction, where we assume the base case P of 1 and we proved the statement P of 1, assumed P of 1 till P of k, and proved Pk plus 1. This is one iteration of the strong induction. We defined a few prime number definitions where a number a and b are said to be a multiplicator of each other if a can be written as bq. The second one was an integer p greater than 2 is called a prime number if the only positive integers that are factors of p are 1 and p. If an integer c is greater than or equal to 2 is not a prime, then there are integers existing that are greater than 2 and less than c minus 1 that can be written as c is a times b. We did a question on proving that any integer greater than 1 can be written as the product of prime numbers. We use the existing definitions that we talked about just now, right here for the two cases. The next was we proved that for any postage stamp of 8 cents and upwards, they can be composed of 3 cents and 5 stamps each. We used the understanding that Pn plus 1 can be written as Pn minus 2 plus 1 3-cent stamp in it, right? And that's how we solve that, right there. Adding one more 3-cent stamp in that. Now the next question was breaking a chocolate bar into pieces. So into individual pieces we needed n minus 1 breaks. It was interesting because there was a first cut that we had, and then it was a recursion where we said, because we had assumed from p1 till pk, any break from k plus 1 will give us 2 chocolate bars of size between 1 and k, and we have already proven that for that we need k minus 1 breaks, so we just add the results to that, right? It's right there. That's what we did. Right, the next thing that we did was for the Fibonacci numbers, that if fn is even, then fn plus 3 is even, right? We just used the inductive hypothesis here, and this was an interesting concept. Then we defined the well ordering principle and how to prove results by using contradiction to them and showing that no subset, there is no smallest element of the set S that satisfies the proposition or the negation of that proposition. And holding that proposition, we could say that the original statement held. This is a question for you. Try to prove that using the well ordering principle. And just last note, stay safe and stay healthy. And I hope you were able to put in your homeworks, and looking forward to hear about any suggestions or anything that you have queries regarding. Stay safe. Thank you. Have a good